Hi, welcome to the first lesson of optics. This is Light, a user's guide. Basically, it's your one-stop overview to what we're going to be doing in this unit and why it works. So the first thing we want to talk about is, what is light? Now, light is an electromagnetic wave. Now, you maybe think of waves on a beach, and waves of light are kind of like that. They have crests and troughs that sort of go one after another off into infinity. Now, we describe light based on the wavelength. What that is it's the distance from one crest to the next. So what's special about light is its electromagnetic waves between about 450 and 750 nanometers. Now a nanometer is 10 to the minus 9 meters. If you were to take the smallest thing on your ruler, a millimeter, divide that by a million, that's a nanometer. So light's really, really tiny wavelengths. Now, there's a lot of other electromagnetic waves we're going to talk about, like radio waves, infrared rays, gamma rays, X-rays. What's special about light is, or visible light, is it's what our eyes can detect. So, where does the light come from? Well, objects that produce light we call luminous. So, for example, the sun, light bulbs, objects that reflect light, this monitor you're looking at, those are luminous. Things that reflect light, so things that, like the moon, that look shiny, but are just shiny because they're reflecting the light of the sun. If the sun wasn't there, you wouldn't see the moon, are called non-luminous. So how does light travel? Well, light travels in straight paths that we call rays. Optics is what we're studying. It's the study of how does light work. And the nice thing is, because it's straight lines, you can actually do this entire unit just by drawing straight lines with a ruler and something we call a ray diagram. So, in fact, you can avoid all the math, well, pretty much all the math in this unit, just by being really good at drawing straight lines. In a vacuum, light travels really fast, or, well, air, in fact, it travels almost at exactly the same speed, so far that it's like about 5 decimal places, so we don't really care at this stage. It travels 3 times 10 to the 8th meters per second. That's really, really fast. That's 300 million meters every second. That's about 4 times around the world in 1 second. That's why we use light for all sorts of fancy communication things like radio and fiber optics. That, in fact, it's why you're able to download this video right now. It's also why I'm able to do this video right now. Now, we can slow it down. In fact, we do it all the time. Whenever light enters a more dense substance, it slows down. So for example, when it goes from air into water or air into glass, the light actually slows down. In fact, we've designed materials that can actually slow light down to about 80 kilometers an hour. Now, we give how much the light slows down a special name. We call it the index of refraction. And that's the ratio of the speed of light in air or a vacuum, c, to the speed of light in the material. So we have an equation on the side. It's not really that hard. You just divide 3 times 10 to the 8th by whatever the speed of light in the new material is. That's your new index of refraction. Now, a lot of the time we might also want to know, well, how fast does it go if I know the index of refraction? And that's typically the math you're going to be doing. So, if we know the index of refraction of water is 1.33 and we want to know how fast it goes, well, we just, first off, write down what we know, that n is 1.33, c is 3 times 10 to the 8th, and we write down that v equals question mark. By the way, that may seem kind of silly writing down what we want you to find, but it's actually the biggest mistake in physics, is solving for something wrong. Then all you do is plug in the equation, rearrange it to make v equals c over n. By the way, I know you may not be good at rearranging. If you're not, please, grab Mr. Cudmore and get him to help you, because, well, I don't mind doing it. I had a lot of trouble with it in high school, but I'm pretty good at it now. So, you got 3 times 10 to the 8th meters per second, plug in the numbers, divide by 1.33, put it through your calculator, you get 2.3 times 10 to the 8th meters per second, or 230 million meters per second. Still really fast, but not quite as fast as it was before. Now, one little thing, that what meters per second and the 10 to the 8th may be a little confusing to you. The 10 to the 8th, your calculator does that for you. You have a box that either says EXP or 10 to the X. All you do is you put in your 3.0, hit that exponent or 10 to the x button, put in 8, hit enter, you're done. So the obvious question is, why do we care? Well, the higher the index, the slower light moves. And what you're going to notice is, in other lessons, this explains just about every optical property of materials. If you want to know why your glasses work, well, this is the reason, is that the glass slows the light down and it bends it slightly. If you want to know why a prism works, well, it's when the colors slow down, they separate. The different wavelengths separate. So everything we're going to talk about is actually due to this index of refraction, and how much does it reflect, how much does it refract, what does it do? And what does it do? Well, when light hits a boundary between two mediums, by the way, medium is what we call whatever light's traveling through. It's not some sort of psychic person. When light hits a medium between two different boundaries, like for example here, air or water, there are a couple things that can happen. It can be reflected, it can be transmitted, or it can be absorbed. If it absorbs or reflects all the light, we call it opaque. If it's translucent, some light gets through, but some of it's also reflected or absorbed. And transparent allows all light to pass through with none of it being reflected or absorbed. Now, in reality, everything's translucent. Things are more opaque or more transparent, but there's no such thing as a perfectly opaque or perfectly transparent material. They're all translucent, sort of leaning towards one or the other. All right, hope this makes sense. Move on to the next lesson.